Good morning, everyone. Welcome to our briefing. We are going to talk about how to attack smart devices using a sound weapon. I'm Wang Zhengbo. Here's my colleague Wang Kang. Next, he will also take this stage. Yang Bo, Li Shangyuan, and Pan Aimin are also our collaborators. They are not here today. Wang Kang and I are members of a research team of Alibaba Security, and our research interest mainly focuses on IoT security, and also we are concerned with AI-related security issues, as well as its combination with IoT. It's the first time for us to come to Vegas. Wang Kang attended a Black Hat Euro in 2015, talked about GPS spoofing. Here's our outline. First, we will give an attack demo of Oculus headset at first. Then we will explain the principle behind that, including the physics principle of MEMS, accelerometer, and the gyroscope, and how to perform attacks. After the in-depth analysis, we have more experimental video about other popular models of VR headset. Then we will go on to show our vast investigations into this vulnerability with even more results on drones and self-balancing vehicles. At last, we have some potential countermeasures to share. As the video shows, a VR headset from Facebook Oculus is placed on the table without any movement. The silver color cylinder on its top is an ultrasound emitter. The virtual world displayed inside the headset is mirrored on the external monitor. When we shoot it with a beam of ultrasound, the virtual world turns unstable and rotating. But it is quickly restored due to another positioning system, the IR camera on the left. After turning the camera away and tuning the emitting frequency carefully, we can manipulate its orientation and even hold it for a while. It's rotating, and I'm tuning. For the right parameters, it will hold for a while. Next, we will explain in detail how we make this happen. Oh, sorry. Tear down the device. And thanks to iFixit.com, we don't need to run our own devices to find out what's inside. You'll find its main board. An ordinary chip seems no difference with others at here. It's a MEMS sensor from Bosch. It provides information of movement of the headset, accelerations, and angular speed, to be specific. Thus, the view can change along with your movement. It is this MEMS chip that we hacked to achieve the previous results. Then, what is MEMS? In fact, MEMS is a very broad concept, means micro electromechanical system. The system can be composed of springs, cantilevers, and even gears. They are fabricated on silicon, polymer, or other materials at micro scales. Here we mainly introduce MEMS accelerometer and gyroscopes. This is a MEMS sensor module. Some of you may be familiar with it. On the module board is a chip encapsulating an accelerometer and a gyroscope inside. This kind of chip are widely used these days. They help VR systems to track the position of the headset, capture user movement in phones and smart watches, keep self-balancing vehicles and drones from falling, and even decide when to release airbags in cars and keep the car steady while it's turning. Of these count up to several billions of devices. That's why we are so interested in its security issue. Take an accelerometer as example. Inside the chip, it looks like this. The photo is taken with scanning electron microscope, SEM. So you can see some beams and comb-like structures and so on. To be clear, let's make some simplification and transform it into schematics. This is a sensing mass. These act like springs. And this comb-like structure form capacitors and are used for displacement detection of sensing mass. In the view of mechanics, the structure is equivalent to a spring mass system of 1 degree freedom. It moves like this. The working principle of accelerometer is pretty straightforward. The sensing mass stays at equilibrium position while the system feels no acceleration. While accelerating, for example, on a roller coaster, a force will pull or push the spring and cause a displacement. Measure the displacement, and we can tell how much the acceleration is. By the way, the displacement is measured by the change of the comb-like capacitors. And this is a one-axis accelerometer. 2 or 3 of such systems can compose a multi-axis accelerometer. For a spring mass system, the resonance phenomenon exists. Under a periodic driven force, the amplitude gets its maximum when its frequency matches a specific value called resonant frequency, which is determined by the mass m and the spring resistance k. Resonating mechanical wave, such as sound wave, can disturb the sensing mass and makes it deviate from its equilibrium position. And the accelerometer will generate force output when there is actually no acceleration. Recently, T-Triple et al. From Michigan University and University of South Carolina realized the sonic tech using resonating sound. Their work was accepted by IEEE European Symposium on Security and Privacy. Combining with the aliasing effect in ADC module, they achieved manipulation of the output. They demoed it with writing letters with output data plot. It is very impressive. After we introduced so much stuff on MEMS accelerometer, let's move on to gyroscopes. Gyroscopes share similar structure with accelerometers. Here is a SEM photo of an accelerometer, and here is the photo of a gyroscope. It looks much more complicated, but you can find similar structures. From an accelerometer, we can construct a gyroscope by inserting it into a big outer frame and bind them with springs. Then, to indicate the displacement, comb-like structures are also required. In this device, the inner comb-like capacitors are not used to measure displacement of the sensing mass anymore, but to drive it into a periodic movement, or to induce periodic displacement. Further simplification can be done like this. Different from an accelerometer, the gyroscope has 2 degrees of freedom. As I just mentioned, the sensing mass is actively driven into a periodic motion like cosine omega 0 t. When there is no rotation, the up and down movement of the sensing mass has no effect to the side-to-side movement, so the offspring stay as the same. When there is rotation, things become different. A force will pull and push sideways, which is so-called Coriolis Force. Later we'll explain. The displacement is measured to indicate the angular speed of the rotation. Intuitively, the displacement d changes along with the inner mass at the same frequency omega 0. So we can write it into the form of amplitude A multiplied cosine omega 0 t. If the amplitude A is positive, that means the out spring is stretching while the inner spring is stretching. This means the system is rotating clockwise. If the amplitude A is negative, that means the out spring is stretching while the inner spring is compressing. The system is rotating counterclockwise. A little more explanation on Coriolis force. Imagine a big plate and a man walking on it. If the plate is rotating counterclockwise, the corresponding angular speed is defined like this, pointing upwards. The man is walking from the edge toward the center of the plate. There will be a force preventing the man walking straight or pushing him sideways. The force is so-called Coriolis force. And its definition is like this. Also, the Coriolis force can also demonstrate with the finger spinner. You can feel its resistance force as you turn it while it is spinning, like this. The displacement oscillating amplitude A is able to indicate the rotating speed. To extract the amplitude A, we can multiply D with the driving signal and then pass a low-pass filter to eliminate the high-frequency term. What's left is amplitude A. Some of you may have found out the method of attack. For the accelerometer under sonic attack, the sensing mass is forced into resonance. For gyroscope, the frame is resonating. And the displacement D is forced to oscillating with the ultrasound, of which frequency and phase are not equal to the driving signal as normal. Here we indicate the frequency using omega u, and with a subscript u stand for ultrasound, and delta phi for phase difference. And AU indicates the induced oscillating amplitude by the ultrasound. Again, we do the math and we'll get the oscillating output. This is the attack output. Here are some special cases. Suppose that omega u exactly equals to omega 0. That is ultrasound frequency equal to the internal driving frequency. Let's see what happens with different delta phi. As the frame is forced oscillating along with ultrasound when the phase difference of the ultrasound and the inner driving signal is between 0 and pi, it will create a force output of clockwise rotation. When it's between pi to 2 pi, the force output is counterclockwise. Of course, for real circumstances, two frequencies cannot be exactly the same. Then the effect phase difference is ramping from 0 to pi, and then from pi to 2 pi. When frequencies differ too much, the output oscillating fast, the resulted attack effect looked like random, which was just the phenomenon observed by the researchers of KAIST from Korea before. Their work appeared at Usenix 2015. To testify our theory, we manipulated the output level of the gyroscope from MPU 6050. This can even be a very simple data modulation scheme. We can probably use this scheme to establish a communication channel. Researchers from Israel have sent secret messages into phones using such channel. Their work appeared at Usenix 2016. We believe our technique can help them to do better. After our in-depth analysis of MEMS gyroscope, my colleague Wang Kang is going to show you our vast investigation of its influence with numerous of videos. So have fun.
Okay, my name is Wang Kang. Wang is my first name, which in our country comes from our ancestors. Wang stands for king, stands for emperor. Kang means rich, means healthy. By the way, my colleague Wang Zhengbo shares the same first name with me, which means his ancestors may also come from a king or emperor. Well, back up to our briefing. As mentioned earlier, MEMS sensors are widely used, so we investigated a wide range of devices, including wearable VR systems, smartphones, and automatic systems such as drones and self-balancing vehicles. This is a demo with Htc Vive headset. As we can see, when the ultrasound emitter is placed near the MEMS sensor, which is indicated by the red arrow on the left picture, it turns unstable and rotating. Similar to Oculus, Vive system also adopts IR camera for position tracking. But in contrast with Oculus, Vive will freeze the interaction if it detects discontinuity between MEMS sensors and IR trackers. And it will also display warnings for users. Then the HTC Vive VR system ships with a pair of game controllers, which is on the right side. And the MEMS chip is indicated by the red arrow. It's quite easy to manipulate when pointed with our ultrasound emitter. We're tuning the frequency. This is the controller image on the VR screen. Another demo, Hololens is an augmented reality device. It will take a while when initializing a so-called spatial mapping process. It takes in environmental features as a positioning reference. Therefore, this attack can only cause some image dithering. It's dithering now. we are switching the resonating frequency. And the dithering frequency is changing. Besides those professional VR systems, there are also many phone-based VR systems, such as Google Cardboard and Samsung Gear VR. So we also tested some smartphones. And this is a Samsung S7. When the ultrasound emitter is on, the VR wheel will be rotating. The ultrasound frequency is around 31 kilohertz, which is the resonating frequency of another axis of its MEMS, so that the rotating direction is horizontal, which is slightly different from the demos before. On. In order to make the effect more easily to be viewed, we attached the ultrasound emitter at the rear of the phone, which is this black speaker-like things. Well then, we also tested with an iPhone. The window of the MEMS sensor in iPhone 7 is EvenSense. We started with the built-in Compass app. When you slide to the second screen in the built-in Compass app, it can be used as a level instrument. It's a very handy function when you have to hang a picture on the wall or something. We put the iPhone 7 on a water level table. Then we generated the ultrasound and placed it near the MEMS chip to see what happens. Well, the vibration amplitude of the bubble on the iPhone screen seems very promising. So what about trying something real? So we tried with Facebook 360 VR. It's just vibrating and vibrating and vibrating. Adding some Doppler frequency shift just by moving the emitter forward and backward very fast. The effect, as we can see, is much stronger. Maybe some real serious hackers can exploit the vulnerability to prevent their children from playing too much of VR games, very likely. Then we are still not satisfied. What about something more interesting? Something can fly, can run, or can stand. So we continued with our journey with drones. Researchers from Korea made the first attempts towards drones using ultrasound, but the experiment is with their DIY drones, and the MEMS chips are nearly exposed. So we took a real commercial off-the-shelf DJI Phantom 3 for testing. For safety concerns, we took the full pedal off so that we can keep our fingers. And as a proof of concept, we took off the case and found the MEMS chips are also from EvenSense, which is the same window from iPhone. As we mentioned earlier, you can hear the noise pitch of the rotors will be changing, which means the spinning speed of the rotors are changing. FYI, the drones adjust their flight states just by changing the RPMs of those 4 rotors. Now we turn on. The flight state is changing now. We think this is still a very experimental way to rock the drone down from the sky. So to accomplish this target, you still have to work out a way that can transmit the ultrasound through a long distance of air and fog and the plastic case of the drone and the aluminum case wrapping the MEMS. We used to think the 5mm thick foam is added just to prevent some hackers like us to prevent us to take advantage of the MEMS vulnerability. The good news, though, is that later we found out that the main purpose of adding the foam around the aluminum case and the MEMS PCB board is to prevent the unwanted vibration from those 4 rotors, not to prevent our security researchers. As you may have noticed, there are also 2 thermal resistant on the PCB board near the MEMS chip. They are supposed to heat the environment temperature inside the aluminum case so that to minimize the influence of the sensor thermal drift. So we think there is still a chance. Although we are not able to rock the drone down, we can prevent the onboard camera from taking pictures of good quality just by shaking the camera. As we know, the vibration introduced by rotors can cause a picture taken from the onboard camera very blur. So the manufacturer have to add self-stabilizing function to the camera. In fact, DJIs are very proud of their self-stabilizing technology. They even made another Steadicam product called Osmo. So we pointed our ultrasonic gun at it. The phone on the desk is receiving video from the drone through the radio channel real time. Well, if someone is taking a footage from a drone or from a Steadicam with MEMS, and somehow you don't want yourself to be seen, maybe this is the exact defense weapon for you. Plus, we don't have a DJI Osmo Steadicam, so I think it's still very interesting to give it a try. Then we focus on something which can run and can stand, a self-balancing robot. We first bought a DIY robot from Taobao.com. The MEMS chip is Aimin's MPU 6050, which is a very popular module in the market. As you may remember, MEMS module from iPhone comes from Aimin as well. We thought it would be a really easy task. Just plug in your power supply, turn on your signal generator, tune to the resonating frequency, emit the ultrasound, and then, no. Out of our expect, the ultrasound showed no effect. At first, we were wondering if the resonating frequency is not accurate. But we even took the MEMS daughter board of the robot, plug it into a Arduino, read numbers directly from SPI interface, and plot some fancy diagrams just to check if the gyroscope is affected. Soon, we found out the gyroscope part was indeed infected. Well, then what the problem could be? After several days investigation, we found out the control algorithm of the robot probably doesn't take gyroscope as inputs. Since MPU 6050 has integrated an accelerometer as well, maybe the algorithm only uses the accelerometer instead of gyroscope. So we switched to attacking its accelerometer part. The high-pitched noise in the background you just heard is the resonating frequency of the accelerometer, which is around 5 kilohertz. It's not in ultrasound band, in fact. It's very, very noisy and disturbing. You better put on some noise reduction earplugs during your own experiment. We also tried with a commercial toy. This is a self-balancing robot from Xiaomi. This is much easier. When the ultrasound is pointed at it, it falls. Or maybe some very serious badass hackers will exploit this vulnerability to make some kids cry. I don't know about that. After the huge success on some serious toys, we also tried with a rail scooter, 9-volt mini, also from Xiaomi. The circuit board is sandwiched between an aluminum structure and a thick battery. It was very hard for us to feed the ultrasound in. At first, just in order to prove the possibility, we planted an ultrasound emitter inside the case, right above the MEMS chips. Still fine-tuning the frequency. Some may think it's not that kind of real issue. People will say you still have to put your emitter so close to the MEMS chip. So what's the point? So we did a lot of experiments after that. And finally, we found that with precisely chosen resonating frequency, and through a very narrow slit on the case, we can feed the ultrasound in and change its motion state. Let me show the result. And just as a proof of concept again, armed with a power amplifier, which is about 5 decibel, a much stronger ultrasound is generated. Well, maybe someone could develop a no scooter zone with this Achilles heel, I think. As we mentioned before, airbag system and ESP system in automobiles is highly depends on MEMS sensors. Even though the car looks strong outside, maybe they also exist such Achilles heel for sound or ultrasound leakage. To sum up, the security concern with MEMS sensor might date back to a report by NASA JPL at 1998. At that time, MEMS is not very popular, used in consumer products. It's understandable that in space mission, noise with high intensity presence, but it's passive and unintentioned. Then in 2007, researchers in the specific field start to notice the resonance-related problem. The first intentional attack towards MEMS using the sonic noise performed by Korean researchers. They found that near resonant ultrasound would render the gyroscope sensor output useless and thus can knock the drones down. It's some sort of denial of service. Recently, MEMS accelerometers output are able to manipulate it by another group of researchers. They combined resonance and the ADC sampling process cleverly. It's very interesting. I think our contribution filled the gap of gyroscope output manipulation. And some countermeasures, such as DJI drones and 9-volt scooter robot, they are armed with multi-layers of shell. Although I don't think they are added by the manufacturer on purpose. Interference ultrasound or sound cannot work without a strong enough power. After penetration, such obstacle, there is hardly little energy left. So the most affordable way is just to put on some shell. However, this is not applicable in case of VR device, because our head cannot afford too much weight. Software may be a better choice, as the frequency is specific. It can be easily monitored. If the intensity goes beyond limit, just warn the user or pause the application. Pretty straightforward. We also found that some chip designers are already trying to figure this problem. They are designing new types of MEMS chips that can resist sonic attacks. Besides, multi-sensor fusion algorithm should be introduced. For example, you can install 2 or 3 groups of MEMS sensors from different vendors. At least they are not so easily failing at the same time. In fact, some drone manufacturers have already taken this way. This is a boom. You can get the whole experiment system within $30, since the maximum frequency required is only about 30 kilohertz. The signal generator in our experiment is some kind of overqualified. You can just replace it with a much cheaper one. Okay, I think there is some time, so I'd like to do a quick real-time live demo. And this is our signal generator, and this is the ultrasound emitter. And now I connect the signal generator to this ultrasonic emitter. And I have already set the frequency to my iPhone, the resonating frequency. Wait a moment. Let me try it before I show it. Oh. Check the amplitude, frequency, and output. Okay, it's working now. Okay, and I think I have to. In order to show you, I have to connect this one forward. Okay, and sorry, I don't know if you can see this. Okay, and you, wait, the sound, the volume. I pointed at this. It's okay. It's still right now, and I just turned it off. It stops. This is the built-in Compass app. And switch it on again, and stop. So we can try it with a Facebook 360 VR. Wait. Sorry.
You will fail at some point in your life.
I don't know why he said that. Okay. Maybe I will fail sometime in my life. I'll turn it on. Right. Okay. Uh-oh. So I don't know if you. Okay. Literally. And it's vibrating now. So if anyone wants to try it for yourself, you can come up to try it with your own iPhone. Okay, that's all. We would like to thank Dr. Sun Yinan from Tsinghua University and Dr. Li Ke for their help. If any questions, I would like to take them. Thank you.